I'm going to introduce Dan McLean. He is the CEO of the PTRC. He's going to talk to you a little bit about PTRC and introduce Rob. Go ahead, Dan.
Thank you, Norm. Good morning, everyone. My name is Dan McLean, president of the PTRC. I'm very excited to be a part of this webinar today. As Norm said, this is our 8th over this period. I would like to just say that these continue to be very difficult times, and I hope that you and your family are staying safe. For us, we continue to work remotely, going into our offices on occasion. I suspect that a lot of you folks are doing the same thing. So I hope you're safe and have some time here today to listen to this very important webinar. The PTRC has been around for well over 23 years. We've been involved in research and technology for energy, primarily in the oil and gas sector. But over the last few years, we have been branching out into supporting what we call energy from the earth. We see complementary skill sets being applied in a lot of things from lithium, helium, hydrogen. And so we have taken an interest in supporting that kind of technology. You're going to hear from Rob Stewart today. He is bringing what I would call a new technology to the forefront. We found it quite compelling, quite interesting. And I'm obviously you also think it's interesting because you're here on this webinar. Compressed air as another energy opportunity fits right into the bailiwick of the PTRC as we're going forward. If you want to hear more about this and other technologies, I encourage you to mark your calendar for May. PTRC is the owner of the Williston Basin Petroleum Conference. That's going to be held in Regina in May. We're hoping it'll be an in-person event, and the theme for that conference is going to be energy from the earth. So you will hear about the whole gamut of research that PTRC has been involved in. So with that, I would like to introduce you to Rob Stewart. His bio is attached to the emails for this webinar, and he is going to tell you about a very interesting technology. So I'll turn it over to you, Rob.
Great. Well, thank you very much, Dan and Norm, for those introductions. I'm very delighted to be here presenting to or with the PTRC, and I appreciate the work that's gone into getting this put together. And I'll see if I can share my screen here so we can get right into it. I've got a fairly lengthy presentation, fairly detailed presentation on compressed air energy storage, trying to cover a lot of material within the time we've got here. So hopefully I'm able to cover enough that everyone's able to understand, but gives enough to everybody who may have a deeper understanding of what we're talking about. So my name is Robert Stewart. I'm president of RMP Energy Storage. We're a Calgary-based energy storage development company. I have a mechanical engineering undergrad from Waterloo, a PhD from chemical engineering from University of Alberta, and I've been working with RMP for over 5 years now on energy storage. So just some highlights to quickly go through, just the things you can pay attention for later on in the presentation or look forward to. So compressed air energy storage, I'll refer to it as CAES throughout the presentation. It's a proven technology. There's multiple existing assets, and it's capable of fully integrating or fully managing renewable energy on the system, the electrical system. We're developing and building CAES plants requires the same trades and workforce as those that we already have within the hydrocarbon industry, specifically oil and gas processing and hydrocarbon storage facilities. Compressed air energy storage, we've done some detailed modeling that enables us to show that a standalone compressed air energy storage facility and wind generation facility are able to provide baseload power at a competitive price to a combined cycle GT with 80% lower emissions and a pathway to zero emissions. One of the interesting things that we've spent a lot of time on is looking at the geology throughout Alberta, Saskatchewan, and more broadly Canada and North America. And something that's become more and more apparent is how suitable the Alberta Saskatchewan geology is for this sort of technology, and how expansive it is, that the opportunity is large enough that we could build as many of these as we need or beyond for export opportunity. So the project that we've been focused on for the last number of years, we call the ASSIST project. ASSIST is Alberta Saskatchewan intertie and storage. It's a 320 megawatt, 60-hour duration diabatic CAES project. I'll explain all those, what they mean in a little bit. And it's on the border between Alberta and Saskatchewan, or proposed for the border between Alberta and Saskatchewan. During construction, there'd be over 1,000 full-time construction jobs and over 30 full-time equivalent jobs going forward during operations. A facility of this size, our modeling would show that it could integrate somewhere between 700 and a gigawatt of wind generation, enabling that to be used as 24/7, 365 baseload supply to the electrical system. The project that we're looking at has a large capital cost of around $730 million and a construction time frame of somewhere between 24 and 36 months. The design one, build many opportunities available, and total right now we're looking for a development budget of around $15 million to get us through the next stages of development. So who we are, so we've been around since 2006 in our current iteration. As I think I said, we're an Alberta-based renewable energy and energy storage development company. We've done a lot of work in the past with solar, wind, pumped hydro, and transmission. And transmission is where our sort of claim to fame is, with the initiation and conceptualization of the Montana-Alberta tie line, which is a large merchant tie line between Alberta and Montana, obviously. We've shifted our focus to be primarily energy storage due to that's where the largest growth opportunities are in our industry, we feel. We're technology agnostic, and we've been looking at compressed air for the last sort of 8 years with the Alberta and Saskatchewan focus in detail. Just gonna have to move this here. Where does that go? There we go. So when we look at what challenge we have right now, there's a lot of things going on within the world in general, but within the energy industry in particular, and electricity industry in specifically. So we've got energy and emissions challenges going forward. And one of the critical things to understand, and forgive me to those who know this already, but electricity is effectively a just-in-time delivery. So when you flick on your light switch, there's a generator somewhere that is ramping up production to increase the flow of electricity to enable that light to be turned on and the system to remain stable. This is really unlike a lot of other industries where you have warehouses, or you have storage facilities for your natural gas, or you have a way to take some product that you produced, put it aside for when the supply or when the demand needs it. This doesn't really exist in most of our electricity system. And in fact, the way that our electricity system has generally been designed is that you build enough generation or supply to meet demand, whatever that might be at any given point in time. Now, renewable energy, they have zero emissions, which is great from our emissions challenge, and they're now very low cost because of the economies of scale that have been achieved, putting them all over the globe. Unfortunately, they aren't always available on demand, and therefore they require management, so that when you do flick on your light, or when you do plug in your toaster or ramp up a machine at an industrial facility, that supply can catch up to you. And you need some way to ensure that if it's not windy or the sun isn't there, that there is something else there to come in and supply that power. that is really the real value of electricity, is that it's available whenever you want it. And it's incredibly powerful. Now, Saskatchewan in particular, there's a lot of changes going on, and the plot on the right here is my thought of one possible outcome that we could see. Right now, we're sitting in 2022. I know that's hard to believe. We've all been in a bubble for the last year and a half or so, but yeah, it's 2022. I have to brush my eyes a little bit for that one. But where we are right now in Saskatchewan is there's a large fleet of coal that's going to be retired over the next 8 years under a federal mandate. There's a target set by the government of 50% renewables and a 40% emissions reduction target below 2005 levels. Associated with the reduction in carbon is the federal CO2 tax that is proposed, and it's supposed to rise to $170 by 2030. And all of this we need to do while keeping electricity affordable and highly reliable. And going back to, this is what the value of electricity is. So what you've seen here on the plot on the right, you see the large black section that is coal, and moving towards 2030, all of that's gone. And one possible alternative is we replace that with a large amount of wind and solar. And that enables us to get to this sort of 50% installed capacity or generating capacity. But you notice that these renewables are variable and intermittent. And so there needs to be some way to manage that, so that they can be able to provide generation on demand, just like these coal plants. So how can energy storage help? So just as I said before, all other energies have some way to manage the supply and demand, and generally this is storage. You know, you have a warehouse, you have a gas facility, you have your freezer and your fridge, you have a water tower. Very similar idea. We want to be able to take energy off the electricity system when it's in overgeneration or in excess, and we want to be able to put it back on when it's in high demand. So what we've got here down below is a plot showing one wind generation facility over a month, and you can see this is actually an Alberta facility because the data is readily available. But you can see that the generation of this facility goes up and down quite dramatically, with multi-day periods of nearly zero production and then multi-day periods of high levels of production. And this makes it very hard to manage this source of energy, even though it is very relatively cheap on a unit of energy basis. The value of it isn't quite the same as other sources. The other thing we've got here is the red line, and that's just a hypothetical load. And you'll see where we're going with this in a minute. So what energy storage enables you to do is it enables you to take some of that excess power when it's overproducing and put it into storage. So now the stark blue line is showing a storage asset. In this situation, it's a CAES asset. And you can see that it's actually able to take the power off the grid when there's excess. You got sort of negative 25 megawatts, you're over generating by a bit more than that. And then when the wind supply is down, it comes in and the CAES plant starts to generate and actually meets that demand during those periods in time. And so what we've got here is a CAES facility providing 1 month of firm supply with the wind generation facility, so that the CAES plant is not a generator by itself. It needs an input energy to be able to provide that service to the grid. It's a storage entity. Your warehouse isn't useful unless you have production to put into it, sort of thing. So what we see here is a very long duration storage asset. And as you can, I'm sure you can realize that if you're operating above a certain period of time for an extended period of time, you're going to need a larger and larger warehouse or longer duration storage to enable that asset to provide the baseload service that you need. And the more volatile your input generation source is, so wind, the longer the duration is that you need for that storage entity to be able to provide baseload supply. And this is really where compressed air energy storage really shines in Alberta and Saskatchewan in particular. Finally, this is just showing on the right, this is onto the right-hand side axis, what is the state of charge of this compressed air energy storage asset that we're modeling here. And we'll come back to this plot again a little bit later. This is just one model of what can happen, but the yellow line is showing the state of charge. So how full that inventory is of energy during these periods. And you'll see what is driving the sizing and selection of the CAES storage capacity. So before I get too much more into how to model this, what is CAES? So CAES is a proven long duration energy storage technology. It's been around since the mid 1970s and conceptually before that. It uses compressors, expanders, and duct burner type equipment that you'd find in many power generation gas plants or other air separation type processing facilities. It also uses subsurface caverns that are purpose built in subsurface geology for storing this air. And the two existing facilities both use solution mined salt caverns. And Alberta and Saskatchewan have the ideal geology and known geology for producing these caverns and for the brine disposal. So really, really high level, how compressed air energy storage works is when electricity is on demand, when it's in oversupply and it's cheap on the grid. You can take electricity, put it into an electric motor. It runs a compressor. This compressor takes ambient air from the atmosphere. It compresses it. Through that process, it heats up the air and you reject that heat. And then that air is stored in these purpose-built storage caverns that are deep below the surface. And in our case, in bedded salt. During the discharge cycle, or when power is in demand from this asset, air is allowed to leave the cavern. It then is heated somehow, and it is expanded through an expander that then drives an electric generator that puts electricity back onto the grid. One difference between multiple types of technologies of CAES, they can generally be separated into a fuel version and a fuel-free version, or diabatic, where you're putting in some form of fuel, and adiabatic, where you're not putting in any fuel. During a diabatic process, this heat is rejected to the atmosphere, and during the expansion cycle, heat is input through either natural gas or some other thermal input. And in our case, this could be natural gas or hydrogen. And with an adiabatic technology, the heat that you've produced during this compression cycle can be stored. And then you can reuse that thermal energy during the expansion cycle. So obviously there's a whole separate component that you need as part of that system for that thermal storage, but enables the system to be 100% emissions free. And that is quite attractive in the zero emissions future. When we look at the resource, there's a lot of salt deposits around the earth, but what's unique in Alberta and Saskatchewan is that we have this large deposit of bedded salt suitable for building salt caverns, and that we've proven we can build salt caverns in for the hydrocarbon industry, is that we also have the ability to dispose of the brine. So during the building of these caverns, you would drill a well. This is a sonograph of an existing cavern in Saskatchewan. So that you drill a well, then you'd start to wash the cavern with water. And so you'd pump water into this well and be pulling it out at the same time. And you'd be controlling the level that water is at so that you're able to build this shape, the desirable shape of the cavern, so that it's suitable for purpose. So whatever you're using that cavern for, you need to design that cavern to be well suited for that shape or for that purpose. And so you control the shape of that cavern by controlling the water flow and a number of other components so that you're able to build up a suitable cavern volume for what you're looking to do. During that process, you're going to be producing brine, so salty water, and getting rid of that brine is actually harder than finding the ideal salt geology. Getting rid of brine is something that probably many of you know very well what to do, and it's been done in the oil and gas industry for decades within the Western Canadian Sedimentary Basin, and therefore Alberta and Saskatchewan has this not only proven salt deposits, but ideal ability to dispose of brine during this process. So while Ontario and the Maritimes have salt deposits that would be suitable for cavern construction, they would need to find an alternative way to deal with that brine. And in some cases they have. There are caverns in Southern Ontario, and they've had to process that brine so that they can build those caverns. Whereas here, we don't have to process it. We can project it into the saline aquifers that exist within the Western Canadian Sedimentary Basin. So a little bit more detail on the Saskatchewan geology. Here you can see the extent of the prairie evaporate salt deposit across the province of Saskatchewan. Obviously, it moves across into Alberta. You can see some little pink stars, and those are showing you where caverns currently exist. I did not make this map, but you can see the link below. It's very good. It enabled us to see from a high level the expected thicknesses of salt, and we're able to build these because we've got a great amount of geological data from all of the oil and gas wells that have been drilled through this geology in the past. That's something that not many other jurisdictions have, and not many have publicly available. So not only do we have the skills here to build these things because we've done it and we use them in the hydrocarbon industry and then the surface facilities as well, we've got the ideal geology, and we know we have the ideal geology because we've drilled so many holes through it. We've also got great wind and solar resource, some of the best in the continental North America. And then the opportunity that is in front of us is also kind of the challenge that we're facing, which is we've got this schedule to retire coal and increase our renewables. And all of these really fit together to making compressed air energy storage a really great opportunity for Saskatchewan to leverage the existing knowledge and skill sets of the workforce and the geology in the province towards a renewable and sustainable future. When you go and you overlay, and this is very, very roughly done, please don't go and cite anything based upon this, but you overlay a map of the SaskPower transmission system, and you can see that a lot of this salt underlays the existing transmission system. Now, building transmission lines is challenging and it's quite expensive, and so we want to be able to try and utilize as much of this existing transmission as possible. And so it is great to see that large amounts of the province, there's potentially suitable salt underneath of it to build caverns, that you can build CAES facilities at some of these transmission nodes within the province, and that's really exciting for us. We're looking up here in Lloydminster. You noticed probably before that it's some of the thickest salt, but that's also because it allows us to integrate a first facility with both provinces, and I'll get a bit more into that in detail. So a lot of people probably thinking, well, how does compressed air energy storage compare to batteries? This is really high level, and it's not meant to cover all scenarios, but generally you can think of lithium ion as a very energy dense energy storage system that is really ideal, providing high amounts of power for short durations, such as in electric vehicles. They're definitely suitable for specific applications on the grid, and for installing and putting in peaking power or transmission alternatives. This is the sort of thing that lithium-ion batteries could be suitable for. Generally, we're looking at something from 1 to 4 hours is sort of the thing that we're seeing in the market right now with batteries, lithium-ion batteries. It's possible that you can go really as long as you want, but the cost increases almost linearly with that duration. So your first hour is the same cost as your second hour, which is the same cost as your third hour. There's a little bit of learning. There's a little bit of economies of scale, but really the cost increase going for an additional hour is substantial. And so once you get up to sort of that 4 hour sort of limit, it's the same sort of cost as a compressed air facility, where you're able to go and build 60 hours of storage because of the ability to just drill another hole and build another cavern. And so once you've got the surface facilities to deal with that brine and build those caverns, the geology is suitable to build multiple caverns. And so doubling your storage capacity from, say, 30 hours to 60 hours is 6% additional cost. So very, very little. Whereas, in a 30-hour battery, it would cost you double that to get to a 60-hour battery, which would be almost 30 times what a 1 hour battery would be. So one other thing is that, compressed air energy storage isn't suitable for smaller scale facilities. It's not suitable for things that are below this line here, so much below 100 megawatts. I don't even think that that's probably worth it economically. Minimum you probably want to go is 150 megawatts, and that's going to really start showing you where you would want to use batteries, the time frame to construct them, the space, the geological requirements. Batteries are very easy to put in. Compressed air energy storage facilities give you this long duration that you're able to build multiple days worth of storage so that you can manage the renewable integration. So how much storage do you really need? This is a question that we've struggled with for a while. We've spent a lot of time with analyzing the Alberta historical pool price, which is the hourly price of electricity, and trying to determine what duration of storage asset would enable us to maximize our return on investment. Going to sort of the other end is, well, how much do you need to be able to provide a baseload service? And this would kind of allow you to understand in the medium life of this plant, so maybe 15 years down the road, when there's not a lot of gas backup on the grid, when there's no more coal, and you want to be able to ensure that this asset can meet demand 24/7, 365, or conversely, capture all of the high-priced hours. So if you had a 4-hour battery on the system, there's no guarantee that you're going to be able to capture the high-priced hours within the pool, and therefore you need to be able to be available all the time to be able to capture those high-priced hours. And that's what this bookend analysis has done. Is it's said, how much duration do I need in a compressed air, an adiabatic, a diabatic, or battery to take a wind facility and enable it to meet a load 24/7, 365. Now, we used Alberta historical wind data, again, because it's readily available and fairly transferable in terms of its volatility, but would love to work with some Saskatchewan specific data in the future. And we've used that to say, how much energy storage do I need? So again, we've got the light blue line showing the wind facility's operation, and we've got now the dark blue line showing, in this case, a diabatic case system operating, and the red line being the load that we're trying to feed. And this is over a full calendar year. And now we see this yellow line coming in showing us the state of charge. And so in the beginning of the presentation, I showed you a plot that was probably about this much. It was most of January, I think. And that really showed that you didn't need all of that duration. But when you cycle through this over the year, what you realize is that what you're really building that duration for is maybe 1 or 2 weeks in the year when wind is really, really low. And it doesn't need to provide that power. A diabatic system could provide power continuously if you needed it to, but the goal of the storage facility is not to provide generation continuously. The goal of the storage facility is to manage that renewable so that it can provide a competitive service on the system. And in this case, that's being driven by a couple of weeks of very low wind generation in the summertime when temperatures are high, air conditioner loads are high. So power prices are likely to be high if you're in a priced market. And you can see the drawdown on this CAES facility with a couple of charging events coming on. And that's what's driving the overall duration of this asset. And the reason why you can get to that duration is because the cost of that additional duration is so small compared to the overall cost of the facility. And so while a battery or a storage facility with less duration would run out here and you would not be able to meet that load, by building that slightly more duration, it gives you that additional certainty. It's like an insurance policy, and it allows you to meet that demand all year round with no backup generation, or conversely ensuring that you can be in the market during those high priced periods. So that's really what's driving you to the long duration. It's not a daily cycle. It's not a weekly cycle. It's over a month or so. The opportunities to charge are less than the opportunities to discharge, and that's driving down your inventory to the point where you're nearing zero storage duration in this model during that event. So how does it cost? How much does it cost? And so again, this is this bookend analysis. This is not. I don't have any insight on costs in the system beyond what's sort of published. But when we look at the facility providing service 24/7, 365 with wind generation, we have to price in the cost of the wind. We have to price in the cost of the gas if it's a diabatic CAES system. And then we're able to see how much that facility would have cost. And what we can see is that somewhere between $30 and $45 a megawatt hour for the purchase price of, sorry, I was trying to drag something here. The purchase price, excuse me, of wind is where we start to cross over with the cost of a new combined cycle gas turbine. And so based upon these gas prices, there's no wind being purchased for this new combined cycle GT. We're looking at somewhere between $50 and $98 per megawatt hour without carbon emissions costs. And for the diabatic CAES system, we're looking at somewhere between $72 and $94 per megawatt hour. And that really shows that this is competitive today. When we include the carbon price and going up to the $170 per ton, what's really interesting is because this diabatic CAES system uses so much less gas than a combined cycle GT, or the CAES plant plus the wind generation facility uses so much less gas than a CCGT, you're achieving 80% lower emissions, which of course means 80% lower carbon cost. And so the cost of that CCGT or CCNG goes from sort of $50 up to $104 at the low end for cost per megawatt hour, and the CAES facility goes up from the $72 to $81 per megawatt hour at the low end of the range. And that's what's really exciting to me for this technology, is not only are you achieving an 80% emissions reduction with known technology that we have the geology and the people to do to build these facilities within Alberta and Saskatchewan, but you're also going to be lower cost in the long term on a bookend analysis. When you look at the flexibility of these types of assets, there's ability to integrate with existing load cycles, existing generation that's already on the grid, in a much greater way when you had the flexibility of a CAES facility compared to that of a combined cycle GT. And you're achieving that with significantly lower emissions, with the opportunity in the future to move towards an adiabatic system where you're higher cost because your input of building that thermal storage component is higher capital cost, but you're able to move in that direction in the medium term. You've built a lot of the infrastructure to build that CAES facility, and the adiabatic system enables you to go to a zero emissions in the medium term. And I think that's what's really exciting about compressed air energy storage, is it's something that we can do today that gets us 80% reduction in emissions compared to a CCGT, and moves towards a zero emissions future. So I'm going to run through these last couple slides pretty quickly so we have some time for some questions. So the projects that we're working on, really high level, I think I went over a lot of this, but our Alberta Saskatchewan intertime storage project that we're developing, we're currently looking for around $15 million to do the next stage of engineering and geotechnical work. It would be 320 megawatts of generation capacity. We're siting it at Lloydminster so that we can provide an intertie between the provinces, a virtual intertie between the provinces. We'd be looking at around 60 hours of duration, and we'd be in very well-known salt geology that's about 1,000 meters deep to the top of the salt, with a thickness of around 140 meters, so that we can build caverns that give us up to 60 hours of duration for this storage asset quite easily. Where we are today is we've currently done a lot of analysis on the geology. We've worked with a number of institutes and research institutions across the country at comparing compressed air to alternatives, as well as looking at the geology in more detail. We've been able to get initial engineering or feasibility level engineering completed, and a lease of space for the location that we're working on. And now we're looking to move to the next stage, which is spending on the increasing geological certainty through core and geomechanical testing that goes along with that, as well as front-end engineering and design. So there's a great opportunity here for Saskatchewan. I just went and grabbed some of the key things that I thought it aligned with in the government's growth plans. And what I see is that there's a lot of similarities between the need to build energy storage and a lot of these growth plan goals. So you need billions of dollars in new processing industry. All of these need power, and all of them want to be low emissions power, and also at the lowest cost and reliable. And that is what one of the big challenges is, and going forward with this sort of growth, is how do you do that? And I think compressed air really enables you to do that. A lot of the interprovincial trade being on the border, allowing this intertie to operate, really enables some additional interprovincial trade between Alberta and Saskatchewan. And it definitely, you can see, enables renewable electricity and hitting some of these sustainability goals. When we look at the direct benefits from the assist facility, we're looking at over 1,000 jobs during the construction period and 30 full-time equivalent for the operational lifespan of the facility. And you can imagine that that's just for the facility. You go and you build this much compressed air, you're going to need to build an amount of wind to go with it if you haven't already. And there's the jobs and the investment and the taxes associated with those wind facilities as well. And this means you're not importing gas from Alberta, you're not importing power from Manitoba or other technologies from other jurisdictions. This is all being done within Saskatchewan, within the tax base of the province. So that's my presentation. I hope that you found that interesting. I'm a little bit over time, but I guess Zinab will help and Norm will help us run through any questions, and hopefully I'm able to give you some more insight.
Thanks, Rob. You can leave that slide up if you want for bits. That way people can get your contact information. So we've had a lot of questions that have come in on the Q&A, but also in the chat room. I think Zainab's been asking some of you to retype them into the Q&A, but what I'm going to do is I'm going to read some of the ones from the chat, and Zainab's going to handle the questions from the Q&A. And those of you, if you've typed it into the chat and you don't think we're going to get to your question, because I'm just going to go from the top on down, make sure you retype them into the Q&A, because those will appear in the Excel spreadsheet. The chat stuff won't. So that's why I always want you to type your questions into the Q&A. Anyway, I'm going to read. So Zainab, if you don't mind, I'll read the first ones right at the very top. These are probably pretty basic questions to start with. We have Paul asking, are there only 2 commercial operating facilities for CAES? And is it possible to replace caverns with storage tanks? Why are you using caverns?
So these are the 2 large-scale operating facilities. There are other test facilities and commercial demonstrations that have been built. I think there's a facility in Ontario, or 2 facilities in Ontario by Hydrostore and Enerstore. Both are under 5 megawatts in size. I think a megawatt or 2. And then there's been tests sort of globally on other smaller scale systems. Many of them have looked at using tanks. The real benefit to using subsurface geology goes back to the benefit that we've been taking from subsurface geology for decades, which is there's this huge volume available to us down there below our feet that we can access and build pressure contained spaces that we can store large volumes of fluids. And in this case, we're doing air, but we've been doing it for natural gas or hydrocarbons for decades. And doing bullets or tanks on the surface simply doesn't get you the duration that makes compressed air compelling, and therefore you'd get a shorter duration, and it wouldn't be cost competitive against, say, a lithium-ion battery.
Good. Zainab, do you want to ask Rick's first? Or?
Yeah, for sure. So a question came in from Dr. Rick Chalaternik. He is wondering about your thoughts on different risk between domal salts and bedded salts for the caverns.
Thanks, Rick. I think you probably have a better answer for this than I do, but I think there's certainly a lot of geomechanical considerations that need to be taken when building a cavern in any geology. Obviously, a domal salt, very generalizing, domal salts in my understanding, tend to have higher uniformity because of the processes they've undergone, and generally they're much thicker, and so you can build much taller and larger caverns. Within the bedded salt, you do have interbeds of other materials that you have to be careful of, and that's why you look at a map over all of Saskatchewan or Alberta and Saskatchewan, you see this huge prairie evaporate. You need to, once you've found a suitable location, you do need to get ground truth, and you do need to check that you don't have interbeds of whether that be a material that's going to prevent cavern construction or damage the wellbore during cavern construction, or a material that might dissolve more quickly than the salt and produce a shape that doesn't align with your purpose. So there's definitely differences. I think that in general, all locations need ground truth before you go and start brining. The benefits of the bedded salt are that it's very expansive, and therefore the opportunity to build these is quite broad across this basin. And now I'm getting outside of my engineering understanding and into a geologist's role, I think. So I'll leave it there.
Okay, good. Zainab, I'm going to read. This appears in both sides, but it's from, and I hope I don't butcher your name. Is it Colum Fury? I hope I pronounced that right. Took me a while to get Kean Healy's name right for rugby, but anyway, is there a challenge in maintaining a constant level of power output from CAES or from CAES as the stored volume of air depletes and the pressure decreases? Is this just managed with understanding the cavern's deliverability and appropriately committing the dispatched energy to the grid?
think you answered it pretty much. But generally, you're going to be having you've got a cavern. This is the project that we're proposing, and in salt, generally, you'd be using a constant volume type of scenario for your salt cavern. So you don't have any hydrostatic compensation, keeping your pressure constant as you would in a hydrocarbon storage facility. And this is because of the deliverability rates that we're looking at require a high flow of air. And you're going to have valves prior to your expander that are going to control the pressure that go into that expander. So your compressor is going to compress up your cavern. It's going to be at a higher pressure than what you're allowing into your expander. It's going to be for a certain amount of time. It's going to be above the pressure in that cavern is going to be above the deliverability pressure of your expander. And then you're right, you're going to start to drop below it. Kind of depending where in your operational envelope for your cavern you place your expander inlet pressure really defines how much time you're going to be at the high end of the operation or the maximum output of that expander versus trailing off. But we're looking at a facility that has 60 hours of continuous output at its nameplate with the diabatic system, and that's because we're supplementing with that small amount of natural gas. I think that answers the question generally.
Okay, there's a question from Chris Patterson. How is the heat stored in the adiabatic process? And why is heat needed to be rejected or added?
Sure. So during compression, heat is generated through the friction and the process of compressing that gas. Excuse me. It needs to be rejected during the compression process. You have multiple stages of compression. This is obviously a simplification. You have multiple stages of compression to get to the desired pressure for the cavern. During each of those stages, you need to reject heat so that you don't melt the compressor internals or don't require very expensive materials in those compressors. So you need to remove heat so you don't go above, 275 or 250 degrees C, something like that. For the thermal storage in an adiabatic system, there's multiple ways to store that heat. And it's one of the things that a lot of people have been spending time on researching and developing improvements. And it's also why the adiabatic technology is not as far forward as sort of the available diabatic system where you're inputting heat during the expansion cycle. And just like during the compression cycle, inputting heat at the back end increases the energy in that air, and that allows you to get more energy out in terms of power. So some of the ways that people are storing heat, some people are looking at it, storing it in pressurized water. Some people have been looking at storing it in things like special purpose built bricks. And there's companies that are looking at storing it in sand or metal like media. And all of these things have either undergone testing or are in process and are suitable for various different locations. Going to extremely long durations like what we're proposing is more challenging with the adiabatic system because of the amount of thermal energy you need to store, and therefore it pushes you towards a selection of a technology that is not going to cost you too much. So using glycol water or a Dowtherm or some special thermal fluid is going to be too expensive at the durations that we're looking at. So you need to go towards one of these thermal storage media that is very cheap to implement at massive scale.
Okay. Lots of questions in here, but this one seems fairly basic. What's the difference between CAES and pumped hydro? Both appear to have long-term energy storage. Is it just the potential energy that is different?
I think that the biggest difference is the siting opportunities. And so pumped and probably the time that it takes to get permitted and build a pumped hydro facility. So pumped hydro is great where you've got the ideal topography for it and the available water, and you're not damaging the existing waterways and ecosystems. I think there's a suitable use of topography and a great energy storage technology that they're quite high efficiency compared to compressed air or an adiabatic compressed air. And obviously they're well proven, but they take a long time to build. There's a lot of potential for cost overruns, as we're seeing even with conventional dams in Canada. And then their siting is really the challenge. So in Alberta and Saskatchewan, or in Alberta, there definitely are very few and far between opportunities for large scale pumped hydro. There's probably a couple of opportunities for pumped hydro type schemes on the existing dams within the Saskatchewan or SaskPower system. I don't know that for sure, but I would think that there's probably some form of opportunity, but the real benefit is with compressed air is you can go to extremely long durations without the need for that topography, and we have the ideal geology. So that's, in my mind, the real big difference. But then you're also not having this large pond of water that you're cycling, and you don't have the hydrological impacts of that system. So there's definitely differences, and the construction time and the siting requirements are primary ones in mind.
Okay, go ahead, Zainab.
Okay, a question came in. What are the material requirement constraints for compressed air energy storage?
Material. Can you read that again? I'm not sure I quite understood.
What are the material requirement constraints for the case?
Material requirement constraints. I don't know if they're referring to the salt material or if they're referring to the thermal storage material. I don't quite know which material they're referring to. So I can touch on the salt. You generally, it needs to be thick enough and it needs to be pure enough that you can dissolve a cavern that's the right shape and is big enough to justify drilling and building the cavern. And then from a thermal storage perspective, it's something that's cheap enough and can hold temperatures up to sort of the 250 degrees C would be ideal, and store it at relatively low cost for long periods of time. And those are the two things that come to mind with that question. Sorry if I didn't get that quite.
No, that's all right. I'm gonna combine two because these are really short questions and probably easy to answer quickly. What's the technology readiness level, TRL, of the proposed project? Is it above 7? If you know TRL rankings, we have to always do that when we're dealing with any application.
Yeah, it's probably a 9.
Yeah, that's what I thought, because it's actually operating, right? So yeah, okay. And then secondly, Eric, my colleague at PTRC, is wondering whether you can also use CAES for leveling the daily variability of solar power if we get large solar farms as well.
Yes, definitely. And so the modeling that we've done it's a bookend, and it's fairly simplistic in its nature. I don't, SaskPower has wonderful systems, and other entities have systems that they can go and model their fleets. I think that you're able to manage any supply demand variability with a CAES facility. Both of these existing facilities that I'm showing, for example, were used to reduce the supply demand imbalance between a thermal generation asset and the local grid. So you had a large coal or nuclear facility, the CAES facility would be able to, and a fluctuating demand profile, the CAES facility would be able to shift those over generation periods to under generation periods. And the same would be the case with a solar facility. I think that solar is a great opportunity for Saskatchewan because of the resource. I think currently it's a little bit higher cost on a per unit energy basis, but it is more certain. And so it becomes part of a good broad mix of renewables, and enables you to really cover some of those periods when you may have that really hot and low wind, but you're going to have sun during those days. So There's some added benefit of having these different sources, and it just requires a little bit more detailed modeling to be able to show that, and probably too complex for here as well. But yeah, definitely it can do that.
Okay, so Zainab, maybe you can ask one more question. I'll just say to people, if your question is in the chat area and you're still with us and it has not been typed into Q&A, please do put it there, because we're just going to answer one more question here, and then the rest we will send to Rob for him to respond to you individually. Okay, so go ahead, Zainab, what more?
Okay. Do you have to maintain the air pressure in the caverns, or can the surface facilities deal with the fluctuations?
So within the cavern, you will have to maintain a certain pressure. The minimal allowable operating pressure of the cavern is defined by the overburden and the stresses within the rock above the salt to maintain the stability of the cavern. And that is controlled all with the surface facilities. The pressure does vary. And so the pressure would go from that sort of minimum up to the maximum. And that is directly in line with where you are in sort of this yellow line of how much duration you have. What's your inventory? So as you can think of this as number of megawatt hours or number of hours of storage, but you can also think of that as very roughly aligned with the pressure within the cavern. Definitely it aligns directly with the mass of air within the cavern. And therefore you're operating between these two bounds, and that's enabling you to keep that facility safe and operate it over long periods of time.
Great, thanks. Okay, so I think I'll have Dan, if he's here, do a few closing comments, and just to remind everyone as well that the questions are being recorded in a spreadsheet. And if when you sign off, there's a 3-question questionnaire, if you'd like to. One of them is to sign up for our newsletter, whether you'd like to or not. We always have to get permission. So please, if you have a few minutes, type in the questionnaire. And Dan, go ahead. Thanks, Rob.
Thanks, Norm, and thanks, Rob. I think everyone can see the synergy between the things that PTRC has been doing from a CO2 storage perspective to compressed air storage. I guess the primary difference may be the focus on salt caverns, but as Robert said, we've got a lot of history using salt caverns for storage of natural gas and various other things. So thank you, Rob, for taking the time to present that to us, and thank you to the audience for participating in this, and lots of questions. And if there are any unanswered questions, Norm and Rob will be happy to answer those. Again, I just want to put another pitch out there for the Williston Basin Petroleum Conference in May. I think Norm has sent you a link to that. We're hoping it'll be an in-person conference. I think we have a drop dead date of the sometime middle to end of February to make that decision. But anyways, thank you all for participating in this, and we look forward to seeing you again at our next webinar. And thank you, Norm.
Thanks, everyone. And thanks, Dan, for being our CEO.